optimizing thermoelectric performance, synthesis and characterization of hydrogenated polymorphous silicon-germanium thin films. Abstract: the search for materials with suitable thermoelectric properties that are environmentally friendly and abundant led us to investigate intrinsic and n-type hydrogenated polymorphous silicon-germanium thin films, produced by plasma-enhanced chemical vapor deposition (PECVD). The attainment of high ZT values, pivotal for effective thermoelectric performance, necessitates the simultaneous optimization of the power factor and minimization of thermal conductivity, a task posing a formidable challenge for material science. This research presents the synthesis and characterization of intrinsic and n-type hydrogenated polymorphous silicon-germanium thin films fabricated via PECVD at 200 degrees Celsius. Specifically, an evaluation of a set of deposition conditions including hydrogen dilution ratio, gas phase germane content, and deposition pressure is reported. Such parameters play an essential role in the electrical properties and materials' structural composition improvement due to the nanoparticle growth inside the thin film, which is a critical factor that enhances the electrical conductivity. Such features demonstrate promising thermoelectric characteristics, underscoring its potential for application in cost-effective and environmentally friendly devices operating near 300 Kelvin. Introduction: hydrogenated polymorphous silicon-germanium is a standard material on microelectronics. Amorphous semiconductors, especially those based on silicon, have a low thermal conductivity but can be used as thermoelectric materials with a high figure of merit if they combine this feature with a large Seebeck coefficient and high electrical conductivity. N-type doping with phosphorus provides an increase in the charge carrier's concentration for hydrogenated polymorphous silicon-germanium, improving its transport properties. Figure of merit ZT is a well-defined metric to evaluate thermoelectric materials and depends on the properties of material. Nowadays, an interest for renewable energy is increasing, so that there is a growing interest in thermoelectrics. Phosphorus-doped hydrogenated polymorphous silicon-germanium is proposed as a possible high-performance material for thermoelectric applications operating near room temperature. Objective: to optimize the hydrogenated polymorphous silicon-germanium material properties, primarily its electrical conductivity, by determining the best deposition parameters for getting a high electrical conductivity material for thermoelectric applications. Experimental stage: polymorphous silicon-germanium samples were deposited by low-frequency PECVD. Results: FTIR analysis was performed on all the samples and the result is summarized in figure at your left. Let us concentrate on the region 480 to 700 inverse cm. 480 cm corresponds to the weak silicon-silicon bond. 560 and 640 cm are for the bending mode germanium-hydrogen and silicon-hydrogen bonds. We can see the evolution of this region as the phosphorus content increases. If we take as reference the area of this region at 0%, we can see that for 1% the area is more or less the same. At 2% this area seems to reduce a bit with respect to 0% P. But at 4% P the area increases, and this is very noticeable. Also is pertinent to note the peak belonging to the weak silicon-silicon bond at 4%. It disappears. The absorption peak at 1,880 cm corresponds to the germanium-hydrogen bond in stretching mode. We can see how it clearly reduces as the phosphorus content increases. For all of the aforementioned, we can say that the phosphorus incorporation reduces the concentration of weak silicon-silicon bonds and enhances the presence of germanium-hydrogen and silicon-hydrogen bonds. Let us remind that the high conductivity obtained for 0% was produced for the depositing conditions and the nanocrystal formation. It is very well known that the nanocrystals help to reduce the weak silicon-silicon bonds, but the addition of phosphorus seems also to behave as a catalyst for this action. We may say that the phosphorus content increases the germanium-hydrogen and silicon hydrogen bonds in their bending mode and reduces the density of the germanium hydrogen bonds in stretching mode. Figure at your right shows the AFM 3D surface images of polymorphous silicon-germanium thin films and depicts the evolution of surface topography of the samples as the gas phase phosphorus content was increased from 0% up to 12%. The mean roughness for doped films reaches its maximum value of 0.6 for nanometers at 4% phosphorus content and decreases if the phosphorus content increases or decreases from this point. Many results in literature were reported for undoped hydrogenated amorphous silicon-germanium, and all of them showed that as the pressure increases, the average roughness also increases. In contrast, our results show that the mean roughness values are always below 0.7 nanometers, regardless of the phosphorus concentration and high deposition pressure. On the other hand, the TEM and STEM mode top view micrographs and EDS spectra shows two facts. First, the large pressure enhances the formation of agglomerates related with silicon-germanium nanocrystals, but the high abundance of hydrogen produced a smooth surface films as it can seen in AFM 3D surface images. And, second, the preferential incorporation of SiGe for silicon-germanium alloys occurs and rapidly saturates more than 90% in solid phase. The figure on the right shows the high-resolution TEM cross-sectional micrograph of polymorphous silicon-germanium sample. The configuration of the grown layers is revealed and is visualized better in the and selected area electron diffraction pattern. Here, fast Fourier transform corroborates the amorphous phase. However, by applying fast Fourier transforms in reduced regions where evident contrast change is detectable will display spectrum with crystalline samples. In other words, fast Fourier transform display well-defined reflections at ~0.17 nanometers, meaning a reflection at the 200 interplanar spacing of the 50-50 alloy. At the same region, nanoparticles of about 4 nanometers in size are visible where localized contrast change is evident. On the other hand, the conductivity as a function of temperature and phosphorus concentration is shown in the figure on the left for the range 300 to 460 Kelvin. From these data, the dark conductivity at room temperature was obtained. The activation energy is derived from a plot of log of conductivity against 1 versus temperature. We can see the increase in conductivity due to the phosphorus incorporation. It reaches a maximum at 4% of phosphorus content and results in conductivity at 300 Kelvin equals to 1.1 per 10 to the minus 1 ohm centimeter to the minus 1. As the phosphorus content in gas phase increases, the conductivity decreases, but in a more or less constant value, in the range of 6.4 per 10 to the minus 2 to 4.3 per 10 to the minus 3 for phosphorus content in gas phase of 6% to 12%. At this point, it is pertinent to say that the depositing conditions of high pressure and high dilution rate promote the growth of nanocrystalline material, i.e., polymorphous material. Furthermore, we can see two distinct slopes in plots of the data of conductivity and temperature, identifying the two-phase structure of the material. The amorphous and crystalline phases, which make a dominant contribution to the electrical conductivity of the material in lower and higher temperature respectively. Conclusions. Phosphorus-doped and intrinsic polymorphous silicon-germanium deposited by PECVD thin films were deposited and characterized. The intrinsic polymorphous silicon-germanium had a conductivity. However, with an untyped doping, the conductivity improved by an order of magnitude, obtaining a material of high conductivity at room temperature. The high hydrogen-dilution ratio plays an important role for increasing the electrical conductivity through the formation of nanocrystals inside the material amorphous matrix. Phosphorus-doped hydrogenated polymorphous silicon-germanium could be proposed as a possible high-performance material for thermoelectric applications operating near room temperature.